Good day, my name is Timothy Adekunle. I'm here to show us the proving of some discrete random variable. I would like to start from binomial. Binomial distribution. This distribution deals with repeated and independent trials of an experiment with two outcomes resulting in either 0 or 1, yes or no, success or failure, true or false. If the interest is on the number of sources and not in the order in which they occur, the probability of exactly x successes in n repeated trials is given by the probability function of a binomial random variable x. This is the probability of having x success in a series of n independent trials when the probability of success in any of the trials is p. That is, our x is the number of success in n independent trials, while p is the probability of success. Proving. If s is a random variable with this probability distribution, then the expected value of x is given as expected value of x equal to summation of x ranges from 0 to n, x probability distribution function of binomial distribution, which is this, where n combination x is defined as this. And don't forget, our q equal to 1 minus p anytime we have q. The second equation shows the expansion of combination, which is n factorial divided by x factorial into the bracket n minus x factorial multiplied by p raised to power x into the bracket 1 minus p raised to power n minus. The third equation, we need to expand the factorial in the equation. Now we want to expand it. In the fourth equation, which is this equation, we factorize np and s divided by x out of the equation. So we now use the method to open this bracket in the third equation. We have this one. So after that, now say that let y equal to x minus 1 and m equal to n minus 1, then n minus 1 equal to x minus 1. We have m here because we said that let m equal to n minus 1. And here we have y because we said that let y equal to x minus 1. The brackets here, we have m minus y. If we look at this place and we look at what we have here, we will see that they are the same thing. So therefore, we represent m minus y with all these things. Let p equal to a and b equal to 1 minus p. The binomial theorem says that bracket of a plus b raised to power m equal to everything a. So therefore, we can turn everything in this place into a plus b raised to power n based on binomial theorem. And we say that a is our p, this plus is this, b is 1 minus p. And if you look at what is a, we can say that p cancel p, remain 1, and 1 raised to power anything is 1. So therefore, everything that is a is 1. Therefore, our expected value of binomial distribution is now np. To prove the variance of binomial distribution, variance of x equal to expected value of x squared minus into the bracket expected value of x raised to power 2. That is to say, expected value of x squared can be expounded as. So therefore, we need to consider the x squared, which is expected value of x into bracket x minus 1, now give us this thing. And based on our proving before, we have x into bracket x minus 1 and n combination x give us this one. Put our p raised by x into bracket 1 minus p raised by n minus x. So everything here is this one. We factorize p squared and n into bracket n minus 1 out with that of x into bracket x minus 1, let y equal to x minus 2 and m equal to n minus 2. Our x squared is now n into bracket n minus 1, close the bracket, p raised to power 2. To calculate the variance, so we just put what we have before into this. By opening all the brackets, we have this one. We just factorize np out. So therefore, the variance of x of binomial distribution gives us np into bracket 1 minus p. Example of binomial distribution. Example 1. A factory produces tools of which 98% are in good working order. Samples of 1,000 tools are selected at random and tested. Question A. Find the expected value that the tool is in good working order and give it a practical interpretation. Question B. Find the standard deviation of the number of tools in good working order in this example. Solution. The probability that the tool selected is in good working order is P equal to 98% according to the question, which we have 98 divided by 100, which gives us 0.98. The probability that the tool selected is not in good working order is 1 minus probability that the selected tool is in good working order. Probability that the tool selected is not in good working order is 0.02. N equal to the number of trials in a binomial experiment, which is 1000. Solution to question A. The expected value according to the proofing is expected value of x equal to np, where n equal to 1000 and p equal to 0.98. So therefore, the expected value is 980. Interpretation. This simply means that in a sample of 1000 tools, 98 tools are expected to be in good working order. Standard deviation. From the proving above, variance x equal to np into bracket 1 minus p. So standard deviation equal to square root of variance, which is square root of np into the bracket 1 minus p. And our n equal to 1000, p equal to 0.98, and 1 minus p equal to 0.02. So therefore, the standard deviation is 4.4272. Example 2 of binomial distribution. Find the probability that at least 5 heads show up when a fair coin is tossed 7 times. Solution. The probability that a head will show up when a fair coin is tossed is P equal to 0.5, because a fair coin has just ordinary 2 sides, and the probability that one of these sides will show up is 1/2, which is 0.5. Therefore, the probability that will not show up is 1 minus 0.5. So P equal to 0.5, 1 minus P equal to 0.5, n equal to 7, the number of trials. Let S be the number of L's that show up. Obtaining at least 5 L's is equivalent to showing X equal to 5, 6, 7. If they say that at least, that is to say it can be more than, they started from that mentioned number, which is 5, 6, 7 till the last number. The probability that at least S equal to 5 equal to probability equal to 5 or 6 or 7 using this formula of binomial. So we have 7 combination 5 in the bracket 0.5 raised to power 5 into bracket 1 minus 0.5 raised to power 7 minus 5 plus combination of 7 combination 6 multiplied by into bracket 0.5 raised to power 6 multiplied by into bracket 1 minus 0.5 raised to power 7 minus 6 plus 7 combination 7 multiplied by 0.5 into bracket 0.5 raised to power 7 multiplied by into bracket 1 minus 0.5 raised to power 7 minus 7. And this combination is expanded here. And the answer for the first one is 0.1641 plus second one 0.0547, third one plus 0.0078, And the probability that at least 5 will show up is 0.2266. Now, Poisson distribution. We want to show how to prove the mean and variance of Poisson distribution. The probability distribution function of Poisson is this. Following the same step in that of binomial, just follow the same step we have, and this one we see, just put the value of PDF, probability distribution function, into it, expand it, and this one is this one. You have it here, expand what they call it the factorial side. We now say that let t equal to x minus 1. Put t in every place we have x minus 1 and factorize lambda out. And this place alone is saying that using the power series expansion of the exponential function, this place alone giving us this. So expected value of Poisson distribution is pi. Proving the experience of Poisson distribution. Follow the same trend we follow in binomial. Just follow the same trend. We have the same thing here. And the variance is lambda. That is to say, variance, mean and variance are the same. Example of Poisson distribution. Ade receive an average of 2 tests every 3 minutes. If we assume that the number of tests is Poisson distribution, what is the probability that he receives 5 or more tests in a 9-minute period? Solution. Let S be the number of tests in a 9-minute period. Then 2 tests every 3 minutes is the average, it's the lambda. So therefore, lambda equal to 3 multiplied by 2. Our lambda equal to 6. Probability that A receive 5 or more tests in a 9-minute period is now equal to x greater than or equal to 5, which is leading us to 1 minus probability that x less than or equal to 4. And this is our probability distribution function of Poisson. So we calculate for each 0, that is, we are going to start from each 0, 1, 2, 3, and 4. When we calculate everything, we have 0.2851. And we say that probability that it is more than 5 or more, is 1 minus probability that it is less than or equal to 4. You can say that 1 minus probability that it's less than or equal to 4. And the probability that receive 5 or more is 0.7149. Thank you. Meet you next time. Please don't forget to subscribe and share.